I prepared a few slides to describe how you can use the experimental data just in case you were not able to attend the Supersonic Wind Tunnel Laboratory. Showing here is the wind tunnel test section. And so you can see it's a Mach 1.8 nozzle. And on the top is the convergent divergent liner. On the bottom is a flat plate. And the double wedge airfoil, which is 10 degree, is placed in the downstream of the test section. You can notice along the flat bottom wall, there are a total of 25 tappings. And so we use these tappings to measure the pressure, static pressure. And also we have two additional pressure tappings on the airfoil, both on the top side, one on the leading edge surface, 27 is on the trailing edge surface. And remember, we have another final channel, which is channel 28, that connects to the settling chamber, which is upstream of the test section, the tunnel inlet. So that channel 28 measures the total pressure. And these are the coordinates of the pressure tappings along the bottom wall. And you can use this to generate your flow simulation domain and compare with the experimental measurement. After measurement, the wind tunnel will output an Excel file, gives you the experimental result. If you open it, the structure looks like this. The first column is the time, which is straightforward. So you can see the reading is every, you have two readings every second, so which means it's 2 Hertz data logging. And then we move further. The first block showing here is about the wind tunnel operation condition. The liner is Mach 1.8. Atmospheric pressure is the pressure during the day. The third column is is a tunnel reference pressure, and that's the air pressure in the feeding pipe. The final column is a model angle. So in here, it's minus 0.1 because during the experiment, we set it as 0 degree. The second block is actually the raw pressure reading. And you can see the unit is bar, and there are a total of 28 channels. And just a reminder, channel 1 to 25 are the pressure tappings on the flat bottom, and 26, 27 are the pressure measurement on the double wedge airfoil. 28 is the total pressure in the settling chamber. Now we move to the blue shaded area. That's the pressure ratio. And you can notice there are a total of 27 columns because area pressure from channel 1 to 27 are the static pressure, and we calculate the pressure ratio between P28 over Pi, I equals 1 to 27, because we take 28th channel as a total pressure. So you have the total pressure over static pressure across the 21st to 27 channels. If we move further to the green shaded area, we can use isentropic relation to calculate the Mach number from the channel 1 to channel 27. So this is the final data you want to use. So if you go through the Excel file for each angle of attack case, you will find the maximum Mach number across your data. So if you plot that as I did in here, and you can find the maximum Mach number along the wall is 1.76. This is for the 0 degree angle of attack case. And also additionally, you can find the Mach number at 26 is 1.65, at 27 is 1.8. And we know in supersonic flow, the double edge airfoil will produce oblique shock waves from the leading edge. It is this oblique shock wave will reduce the Mach number from 1.8 to 1.65. Of course, you can use experimental data to compare with your simulation at zero point 0.6 and 7, and also additionally you can compare the pressure distribution from channel 1 to channel 25 along the lower floor, because in the simulation you can simulate everything. And don't forget about the theory. So the design Mach number of this nozzle, supersonic nozzle, is 1.8. If we use the aerodynamic calculator, the flow turning angle in here is 5 degrees, and we can find, according to theory, the Mach number at channel 26 should be 1.627. That's 1.63, which is very close to 1.65. And so in order to complete your report, if you compare the theoretical value with the experimental value or with the simulation value, you need to explain why there is a small discrepancy. And I don't explain in here, but I leave the job to you.